Something extraordinary is happening right now in the world of technology, and most people have absolutely no idea. While the rest of the world was busy scrolling through social media, catching up on the latest celebrity drama, or worrying about the price of groceries, a quiet revolution was unfolding inside a laboratory in Santa Barbara, California. A revolution so profound, so fundamentally world-altering, that the scientists involved struggled to find the right words to describe what they were seeing. And then, almost by accident, an artificial intelligence called Grok began to read the signals hidden in plain sight, and what it found stunned even the people who built it. To understand why this matters, you need to go back. Not too far, but far enough to appreciate just how steep the climb has been. For decades, the dream of quantum computing existed mostly on whiteboards and in the imaginations of physicists who were told, again and again, that what they were chasing was impossible. Not difficult, not expensive, impossible. Classical computers, the kind sitting in your pocket right now, the kind running every website, every bank, every hospital system on Earth, operate on a simple principle. Every piece of information is either a 1 or a 0, on or off, yes or no. It is binary, and it is the foundation of every digital thing humanity has built in the last 70 years. Quantum computers are something else entirely. They don't play by those rules. In a quantum system, information can exist as a 1 and a 0 simultaneously, in a state physicists call superposition. Imagine flipping a coin, but instead of landing heads or tails, it spins in the air forever, being both at once until the moment you look at it. That is, in the crudest possible terms, what a qubit does. And when you link multiple qubits together through a phenomenon called entanglement, something almost magical happens. The computing power doesn't just add up, it multiplies, exponentially. A system of 300 entangled qubits has more possible states than there are atoms in the observable universe. That is the promise. That has always been the promise. But for most of the history of quantum computing research, the promise remained just that, a promise, because the universe, it turns out, doesn't like to be watched. The moment any quantum system interacts with its environment, even a single vibration, even a stray photon, the superposition collapses. The coin lands. The calculation fails. Scientists call this decoherence, and for a long time it was the wall that nobody could get past. Then came Google. Google's quantum computing journey didn't begin with Willow. It began years earlier with a chip called Sycamore. In 2019, Google made headlines around the world when it announced that Sycamore had achieved what the company called quantum supremacy. The claim was audacious. Sycamore had completed a specific mathematical calculation in 200 seconds that Google said would take the world's most powerful classical supercomputer 10,000 years. The announcement hit the technology world like a thunderclap. Critics immediately pushed back, arguing that the problem was artificially constructed, that the comparison wasn't fair, that classical computers could do better if optimized properly. And in some respects, they were right. But even the critics couldn't deny that something important had happened. A line had been crossed, even if the battle over where the line sat continued for years. What followed Sycamore was a period of intense, often invisible work. Google's quantum team, brilliant, obsessive, deeply motivated researchers, went back to the fundamentals. They didn't just want to win a benchmark. They wanted to build something real, something that could actually be used. To do that, they had to solve a problem that had haunted quantum computing since its inception, a problem so fundamental that cracking it would be considered one of the greatest scientific achievements of the modern era. They had to solve quantum error correction. Here is why that matters. Qubits are fragile, extraordinarily fragile. Any noise in the system, temperature fluctuations, electromagnetic interference, even the act of measuring the qubit itself, introduces errors. In classical computing, you can simply copy data and check for mistakes. In quantum computing, you cannot copy a qubit. It is a fundamental law of quantum mechanics called the no-cloning theorem. You cannot make a backup. You cannot simply check. So engineers developed elaborate schemes to spread quantum information across multiple physical qubits, creating what they call logical qubits, redundant, error-tolerant constructs that could survive the noise and chaos of the real world. The problem was, historically, the more qubits you added to a system to correct errors, the more errors you introduced. It was a vicious cycle that seemed to have no exit, until Willow. Willow is Google's latest quantum chip, and what it demonstrated changed the conversation entirely. For the first time in the history of quantum computing, the chip showed that adding more qubits actually decreased the error rate. The relationship flipped. The cycle broke. Below a certain threshold of error, per operation, the system became self-correcting. It stabilized rather than collapsed. This had been theorized for nearly 3 decades. Every major textbook in quantum information science had described it as a necessary goal and a holy grail, and Google achieved it. The numbers that came with the announcement were almost too large to process. Willow, operating with 105 qubits and an average coherence time of 100 microseconds, 5 times longer than previous generations, performed a standard benchmark computation in under 5 minutes. The same computation on the fastest classical supercomputer available today would take 10 septillion years. 10 septillion. That is a 1 followed by 25 zeros. It is a number so enormous that writing it out on paper would require more space than this script has words. It is a time frame so vast that our sun will have died, exploded and cooled to a black cinder before the classical computer finishes the first trillionth of the calculation. Now, to be fair, and this is important, the benchmark in question is not a real-world problem. It is a mathematical test designed specifically for quantum systems. Google's critics, and there are legitimate ones, point out that this kind of benchmark doesn't necessarily translate directly into useful computation. And they are right to raise that point. The gap between we performed an extraordinary benchmark and we solved a problem that matters to medicine or climate science or cryptography is still significant. Google openly acknowledges this, but the error correction breakthrough is not a benchmark artifact. It is a fundamental physics result. And that is what makes Willow different from everything that came before it. This is where the story gets even more interesting. Because while Google was making history inside its Santa Barbara lab, something else was happening simultaneously on the other side of the AI world. Grok is the artificial intelligence system developed by xAI, the company founded by Elon Musk. Unlike some AI systems that are deliberately kept narrow or constrained in what they will engage with, Grok is built to be direct, curious, and willing to explore uncomfortable questions. It reads voraciously, it synthesizes at scale, it looks for patterns in data that no single human researcher could possibly track across thousands of documents in real time. And when researchers and journalists began pointing it at the enormous body of public information surrounding Google's quantum program, the patents, the research papers, the infrastructure filings, the academic collaborations, the hiring patterns, the supply chain signals, what Grok assembled was remarkable. It is worth being precise here because the internet has not always been precise about this. Grok did not hack Google. It did not access classified files or read internal memos that were never meant to be seen. What it did was something in some ways more impressive and more unsettling. It read everything that was already public, everything that was technically available to anyone with a library card and enough patience, and it connected dots that no human team had managed to connect. The picture it assembled suggested that Google's quantum roadmap was further along than the public announcements implied, that the Willow chip was not a destination, but a waypoint, that the architecture underlying it pointed toward a next generation of quantum processors with dramatically extended qubit stability and error rates low enough to begin tackling genuinely useful, real-world computational problems. One of the patterns Grok identified, and this is where things become genuinely strange, involved anomalous data in the outputs from Google's Sycamore processor during routine calibration runs. There were patterns in the noise, not random fluctuations, but structured, repeating signals that appeared in places where pure randomness was expected. When physicists at institutions including MIT and Stanford were alerted to these findings and began examining the data themselves, the response was measured but serious. These anomalies were not immediately explained. They didn't fit neatly into existing models. Several researchers described them as hinting at physical phenomena that current quantum mechanics doesn't fully account for. Whether this represents a genuine new discovery or a measurement artifact that will eventually be explained away is still an open question. But the fact that an AI found it, flagged it, and triggered formal investigation by multiple independent research institutions is itself a story worth telling. Because this is what AI systems like Grok are beginning to do. They are becoming scientific instruments in their own right, not just tools that help humans work faster, but systems capable of perceiving patterns in data that human cognition simply cannot track. The human brain is extraordinary, but it did not evolve to simultaneously parse 10,000 research papers and notice a subtle statistical anomaly in the 37th calibration run of a cryogenic quantum processor. Grok, in this case, effectively functioned as a kind of scientific antenna tuned to frequencies that human researchers were not listening for. The implications of this expand quickly in multiple directions, and each direction is worth following. Start with medicine. One of the most tantalizing applications of quantum computing has always been molecular simulation. The behavior of molecules is inherently quantum mechanical. Classical computers can approximate it, with enormous effort and significant inaccuracy. A sufficiently powerful quantum computer could simulate molecular interactions directly, with precision. What this means for drug discovery is difficult to overstate. The process of developing a new drug currently takes, between 10 and 15 years and costs somewhere between $1 and $3 billion. And that is for drugs that succeed. The majority of drug candidates fail, often late in development, after most of the investment has already been made. Much of this failure happens because our models of how molecules interact inside the human body are too crude, too approximate. I miss things. A quantum computer capable of true molecular simulation doesn't miss those things. It doesn't approximate, it calculates. The potential to compress drug development timelines from a decade to a few years and to dramatically increase the success rate of candidates that make it through development represents one of the most direct and measurable benefits imaginable. Then there is materials science. The entire history of human civilization could be written as a history of materials: stone, bronze, iron, steel, silicon. Each new material unlocked new capabilities, new industries, new ways of living. Quantum computing offers the possibility of designing materials from the atomic level up, specifying exactly the properties you want, and working backward to the molecular structure that would produce them. Room temperature superconductors, long theorized and never achieved, could transform energy transmission. Next generation batteries could store 10 times the energy of current lithium-ion technology. Catalysts for carbon capture, engineered with quantum precision, could play a role in reversing the damage done to the Earth's atmosphere. These are not science fiction scenarios. They are the natural endpoints of the roadmap that Google's Willow chip has moved significantly closer. And then there is the conversation that makes governments nervous: cryptography. Almost every piece of sensitive digital communication in the world today is protected by encryption. The encryption that secures your bank transactions, your medical records, your private messages, your national security. Communications, all of it rests on a mathematical foundation that depends on one crucial assumption: that certain mathematical problems are so hard to solve that no computer could crack them in any practical time frame, factoring very large numbers into their prime components, for example. A classical computer would take longer than the age of the universe to factor a sufficiently large number. A quantum computer, running a well-known algorithm called Shor's algorithm, could do it in hours. This is the reason that every major government in the world, every intelligence agency, every financial institution that understands what is coming is in a race to develop what cryptographers call post-quantum encryption, new mathematical frameworks that quantum computers cannot break. The National Institute of Standards and Technology in the United States finalized the first batch of post-quantum cryptographic standards in 2024. Other governments are following. But the transition is slow, legacy systems are stubborn, and the uncomfortable truth is that bad actors, state-sponsored, hackers, criminal organizations may already be harvesting encrypted data today with the intention of decrypting it once quantum computers become powerful enough. This is sometimes called harvest now, decrypt later, and it is not a hypothetical threat. It is an acknowledged operational strategy. What Grok's analysis suggested, and what the Willow chip's performance began to confirm, is that the timeline on this threat has potentially moved forward. The conversation that security professionals were having about quantum-resistant cryptography as a problem to solve in 10 years may need to be a conversation about a problem to solve now. Google's own team has been transparent about where they stand. The Willow chip is a research milestone, not a weapon or a commercial product. The number of qubits required to actually break current encryption using Shor's algorithm is in the range of millions of logical qubits. And a logical qubit, remember, requires many physical qubits to construct. Willow has 105 physical qubits. The gap is still vast, but the error correction breakthrough changes the calculus on how quickly that gap can be closed, and Grok's pattern analysis suggested that Google's internal roadmap toward that scale was progressing faster than the published literature implied. It is worth stepping back for a moment and asking a question that doesn't get asked enough in these conversations. What does it mean that we have built an AI system capable of reading the entire corpus of a scientific field and identifying patterns that human experts missed? Not assisting human experts, not summarizing what human experts found, actually discovering something new. The philosophical implications of this are significant and strange. Science, as a human institution, has always been built on a particular kind of intelligence, one that is patient, rigorous, creative in specific ways, deeply social, and fundamentally limited by the bandwidth of individual human minds. Scientific progress happens at the speed of human thought, human collaboration, human communication. Grok and systems like it operate at a different speed entirely. They don't get tired. They don't have research funding pressures that shape what questions they ask. They don't have rivalries with other labs that prevent collaboration. They read everything, and they read it constantly. This creates a new kind of scientific entity, not a scientist, not a tool, but something in between. A system that can generate hypotheses worth investigating, identify anomalies worth examining, and synthesize fields that human researchers have kept artificially separate. The anomaly detected in Google's Sycamore data was found precisely because Grok was doing something no human team would do: reading calibration reports from a quantum processor alongside theoretical physics papers, alongside infrastructure filings, alongside patent applications, simultaneously looking for coherence across all of it. The response from the scientific community was, to its credit, appropriately cautious. No one immediately declared that the laws of physics had been rewritten. The anomalous patterns were flagged, investigated, replicated in some cases and not in others, and the debate continues. But the fact that the debate is happening at all, triggered by an AI's pattern recognition rather than a human researcher's intuition, represents something genuinely new in the sociology of science. There is also the geopolitical dimension of all this, which is impossible to ignore. The race for quantum advantage is not just a corporate competition between technology companies. It is a national security issue that multiple governments treat with the same seriousness they would apply to nuclear weapons. Development. China has invested enormously in quantum computing research, with facilities in Hefei, Shanghai, and Beijing that rival anything in the West. The Chinese National Quantum Lab recently unveiled a portable quantum computing prototype, a development that would have seemed like science fiction 10 years ago. Russia, the European Union, Japan, and South Korea all have major national quantum programs. And the United States, despite having Google, IBM, and a constellation of well-funded startups, is not complacent. The reason this competition is so intense comes back to the same applications we already discussed, but viewed through a different lens. Whoever achieves practical quantum advantage, first doesn't just win a technology race, they gain the ability to simulate materials and develop technologies that competitors cannot yet imagine. They gain the ability, eventually, to break encryption systems that protect their adversaries' communications. They gain a scientific and economic edge that could, in principle, persist for decades. This is why the announcements coming out of Google's Quantum Lab are not treated as mere corporate press releases by people who work in intelligence and national security. They are treated as strategic developments. What Grok surfaced in its analysis of Google's public data touched on all of these threads simultaneously. The patterns it identified in the research trajectory, the hiring patterns at Google Quantum AI, the infrastructure investments, the academic partnerships, all of it pointed toward an organization that was not merely doing interesting science, but was running, with considerable urgency, toward a specific destination. What that destination looks like, and when they arrive, is not something anyone outside the project can say with certainty. But the direction of travel is legible to anyone paying close enough attention. And Grok was paying closer attention than anyone. It is also worth talking about what happens after, not just to Google, not just to the technology industry, but to the broader shape of the world. Quantum computing at scale doesn't arrive gradually and politely. It arrives with a kind of discontinuity that makes traditional forecasting very difficult. When the error correction problem is fully solved, when the qubit count scales into the thousands, and then the millions of logical qubits, the capabilities that become available don't grow linearly. They explode. Drug discovery pipelines that currently take 15 years could compress into one. Materials that currently take decades of laboratory trial and error to develop could be designed on a computer in an afternoon. Financial models of extraordinary complexity could be run in real time. Climate models with resolution fine enough to predict weather at the neighborhood level years in advance could become standard tools for policymakers. And the encryption question doesn't resolve gracefully. There is no smooth transition from a world secured by current cryptographic standards to one secured by post-quantum standards. Every system that has not been updated is instantly vulnerable. The scale of that transition, across every government, every bank, every hospital, every piece of critical infrastructure, is enormous. And it needs to happen before the quantum computers capable of breaking current encryption actually exist, not after. Because once they exist, the window to transition is not months or years. It may be days. This is the context in which Google's Willow chip and Grok's analysis of it need to be understood, not as individual news stories, not as impressive science for science's sake, but as early signals of a technological transition that will be as disruptive as the invention of the internet, possibly more so, and that is moving faster than most public discourse acknowledges. The scientists working on these problems are not, for the most part, frightened people. They are excited people. They are doing the work they trained their whole lives to do, pushing at the edge of what is known, thrilled by each incremental breakthrough. But the thoughtful ones are also clear-eyed about the stakes. Hartmut Nevin, the founder and lead of Google Quantum AI, has spoken publicly about the importance of using this technology responsibly, of developing the applications that benefit humanity first, of working collaboratively with governments and standards bodies to ensure that the cryptographic transition happens in an orderly way. These are the right instincts. Whether they can be translated into the right outcomes in a world where multiple nations and multiple organizations are all racing toward the same destination with different values and different intentions is the question that doesn't have a comfortable answer. What Grok revealed about Google's quantum chip is, at its core, a story about the compounding of intelligence. An AI system analyzing a quantum computing program, finding patterns that trained human scientists missed, triggering investigations that advance the science, which in turn advances the AI, which is better able to analyze the next generation of quantum research. This loop is already turning. It turned in the calibration data from Sycamore. It turned in the patents and papers that fed Grok's analysis of Willow. It will turn faster as both the AI systems and the quantum chips improve. We are not at the end of this story. We are not even close to the middle. What we are at is the point where the story becomes legible enough to tell, where the shapes emerging from the noise are clear enough to describe, even if their final outlines remain uncertain. Google's Willow chip proved that the error correction problem can be solved. Grok's analysis proved that AI can perceive the trajectory of a scientific program in ways that individual human researchers cannot. Together, they sketch a picture of a near future that is genuinely difficult to fully imagine. Because imagination, like classical computing, operates within certain constraints that the technologies we are building are beginning to transcend. The computation that Willow performed in 5 minutes, the one that would take a classical supercomputer 10 septillion years, is a number that human beings cannot feel. We can read it, we can write it, we can say it out loud, but we cannot feel it the way we feel the difference between a cold day and a warm one, or the weight of a stone in the hand. And that gap between what we can measure and what we can feel is in some ways the defining feature of the moment we are living through. The technologies arriving now are not just bigger or faster versions of what came before. They are different in kind. They operate by rules that are not intuitive, that do not map onto ordinary human experience, and that produce outcomes that no single mind can fully trace. This is not a reason for despair. It is a reason for attention. Careful, sustained, serious attention. The kind of attention that asks not just what these systems can do, but what they should do, who decides, who benefits, and who bears the risks when things go wrong. Those questions deserve the same rigor and creativity that went into building the chips and training the models in the first place. The story of what Grok found in Google's quantum data is a story about intelligence, artificial and human, colliding with the deepest mysteries of the physical world and finding, to everyone's surprise, that the mysteries are deeper than expected, and that the tools for exploring them are more powerful than anyone predicted. That is not a shock. That is an invitation. And the people paying attention are already walking through the door.